In this lesson, we're going to start talking about how to compute basic derivatives. So by the end of this lesson, you should be able to answer the following little question. How can we find the derivatives of basic functions? And by the end of Unit 2, we're going to be answering two big questions. How do we make finding derivatives easier, and what is the point of finding derivatives? So Unit 2, Unit 3, we're going to be answering the same two big questions. All right, let's start with the warm-up. So what is the limit definition of the derivative? Remember we did this in lesson 6. So it's the limit as h approaches 0 of f of x plus h minus f of x all over h. In words, a derivative we can describe as the slope of the tangent line to a curve, or the instantaneous rate of change of a dependent variable with respect to an independent variable. Okay, and then for a quick picture that represents the derivative, if I were going to draw a picture, I would draw a curve with a tangent line at some point. So we have f of x, and then I would say f prime of x is the slope of this line as it moves along f of x. Okay, so in the previous lesson, at the end of Unit 1, we talked about derivatives in a very conceptual way. So we were sketching graphs, we were talking about linearizations, we were doing a very applied conceptual estimation sort of approach. Now we're actually going to look at how to calculate them exactly using algebra. So as a first example, we're going to actually compute the derivative using the limit definition. So we want to show that the derivative of x squared plus 1 is equal to 2x. So we always start here by writing our problem statement, so the derivative of x squared plus 1. And our first step is going to be to apply the limit definition to this function. So what that means is our function f of x is equal to x squared plus 1. And so if we want to find f of x plus h, I'm going to plug x plus h in for x. And from that, I'm going to subtract f of x, so that's x squared plus 1. And then I divide everything by h, and I have the limit as h goes to 0. Okay, so where can we go from there? Well, what I could do is I could expand out this squared binomial. So I'll get the limit as h approaches 0 of x squared plus 2xh plus h squared and then plus 1. Then I can distribute this negative to both terms of the x squared plus 1. So I'll have minus x squared minus 1. And all of that is over h. Now, to get from this second step to the third step, I notice that the positive 1 and the negative 1 will add to 0, as well as the x squared and the negative x squared. And so that leaves me with 2xh plus h squared on the top, which is exactly the same as this third step. Okay, so where can I go from here? Well, my goal is to cancel this h in the denominator because that's the issue with my limit of h going to 0. I can't evaluate it with direct substitution yet because the denominator is still 0. So what I can do is I can factor out an h from the numerator. So we have the limit as h goes to 0 of h times 2x plus h all over h. I can cancel the two h's, and I get the limit as h approaches 0 of 2x plus h. Finally, I can actually take the limit now and plug in 0 for h. So we have 2x plus 0, and that leaves me with 2x, which is exactly where I wanted to get. Okay, so that was how to use the limit definition of the derivative. Now, it is important to note that this was a relatively easy function to do this with. On a test, it could be any sort of function, really. There's a couple we won't do because they're too hard, but be sure you know how to do this sort of algebraic process for the next test, okay? There's plenty of practice in the pre-recitation prep as well as in your WebAssign homework. Okay, so now that we've seen how to do the limit definition of the derivative, we kind of want to talk about the derivative as an operation. So just like adding or subtracting or multiplying or dividing, we want to think about taking the derivative as the operation of differentiation. Also, it's in our interest to commit a few basic derivatives to memory so we don't have to use that drawn out process of the limit definition always to find derivatives. So what you have on this page is a table of a bunch of different types of derivatives, and it's important that you commit these to memory, and that's the best explanation I have for that. But we're going to look at some examples next. So our first example is find the derivative of f of x is equal to cosine of x plus e to the x. So we start by writing our problem statement as usual. Our next step is to take the derivative of each part of this function. So we write f prime of x is equal to the derivative of cosine plus the derivative of e to the x. Okay, so what we've done here is we've distributed the derivative across a sum. Okay, and then we take the derivative of each of those terms, and so we get that f prime of x is equal to negative sine of x plus e to the x. Now those values just come from the table, so if we go back and look at cosine, we see the derivative is negative sine, and if we look at e to the x, we see that the derivative is e to the x, so that's where that's coming from. But like I said, you want to make sure by the time you get to on your homework, you want to try to not use the table as much as possible. It's there to help you at the start, but you will not have this table on a test. Okay, I guess the eraser is being kind of slow. Oh, come on. Please scroll. Okay, there we go. All right, so we take each derivative term by term. So the purpose of this first example was to demonstrate the first property of derivatives, which is the derivative of a sum is the sum of the derivatives. So the derivative of a sum is the sum of the derivatives. And this is illustrated in this second step here, where we were able to distribute that operation of differentiation across a sum. Okay, now why would this rule make sense? Well, derivatives are defined with limits. So derivatives are limits. And we did this with limits when we did direct substitution. So when we directly substituted limits, we were kind of taking for granted that we were taking the limit of each individual term when we were substituting those x or t or whatever value was the independent variable. So the second property of derivatives we're going to look at in this next example. So now we want to find the derivative of f of x is equal to 3 times log base 4 of x. So again, we start by writing our problem statement. Now we take the derivative of this function. So the way that's going to work is we can pull this 3 to the outside because it's a coefficient, and I can actually just focus on the derivative of that log base 4 of x. So we can say coefficients are pulled outside of the derivative. So they're still there, we just don't have to worry about actually taking the derivative of a coefficient. Okay, so if we go up to the table and we look for log base A, that derivative is 1 over x times the natural log of the base. So that's precisely what we do in this third step. So notice we've just followed that formula for log base 4. So we can say take each derivative. And notice that that 3 is still there. It kind of just goes along for the ride. So the 3 is still outside. It's not that we get rid of it, it just gets pulled outside of the function so that the derivative is a little bit easier to think about. So again, this demonstrates the second property of derivatives, which is the derivative of a constant times a function is the constant times the derivative of the function. So again, that just means we can take coefficients and pull them outside of that derivative operator. Okay, and why does this make sense again? Well, same reasoning as the first one. Derivatives are defined with limits. And we did this with limits with direct substitution. So once again, we didn't explicitly talk about that when we were doing direct substitution, but we reasoned that it was okay to kind of just plug in an x value because a limit was approaching a y value. So it's similar reasoning here. So since we could do it with limits, we can also do it with derivatives. That makes perfect sense. Okay, so next let's talk about a slightly more difficult type of function. We have a piecewise function here. So we have f of x is equal to negative cosine of x if x is less than pi over 2, and positive sine x if x is greater than or equal to pi over 2. Okay, so since both pieces of this piecewise function are trigonometric, they are continuous. So if that doesn't sound familiar, go back and look at lesson 5. Okay. However, if we were to check at pi over 2, which is the one place they could be discontinuous, we get negative cosine of x, so negative cosine of pi over 2 is equal to 0, whereas sine of pi over 2 is equal to 1. So those two are not equal, so f of x has to be discontinuous at x is equal to pi over 2. Okay, so let's graph this function f of x. So first I'm going to start with the negative cosine function. So maybe I should mark off my axes. Okay, so this is going to be a little bit of a pre-calc review, but we have a period of sine and cosine at 2 pi, so I'm going to mark off pi and 2 pi. I'm going to mark off the little midpoints in between there, and do the same thing on the negative side just so we fill up our whole graph. We have our 2 in between. Okay, so our point of interest is pi over 2, so we're kind of like keeping an eyeball around this general area right here. Oh, come on, pin. It's being very slow today. Okay, so we're keeping a general area around this guy right here. So if we think about how to graph negative cosine, we know that normally cosine would start up at positive 1, but since we have negative cosine, it's going to flip over the x-axis. So our first point we're going to graph at 0, negative 1. And instead of going down like we normally would with cosine, we're going to go up to pi over 2. So we're going to graph an open circle at pi over 2. Since we have that non-strict inequality there. Or no, it is a strict inequality. Yeah. So it's strictly less than pi over 2, so we have an open circle. And then I can continue graphing that negative cosine in the other direction. Okay, so our curve for negative cosine looks something like that. And then for sine, sine we normally start at the origin. So I'm going to erase part of this graph, but the idea is we go up, and then we go down, and then we go all the way down, and then we go back up. So the only part of this curve that we need is actually this part, because we want things greater than or equal to pi over 2. So I can erase that open circle at the origin. Okay, so that's my piecewise function. Now remember, this right here is the area of interest, because that is my discontinuity, and that's going to play into what the derivative looks like. So for the most part, computing the derivative of this is going to be very similar to what we just did. So we can say f prime of x is going to be equal to the derivative of each of the branches. So the derivative of negative cosine would be sine of x, and the derivative of sine of x would be positive cosine of x. Okay, now the tricky part comes in writing these bounds. So sine of x is going to be for x less than pi over 2, and cosine of x is going to be for x greater than pi over 2. So you might be wondering, why did we get rid of the equal sign in the inequality? So right here, that's a bit different than that greater than or equal to in the original function. Well, it all has to do with the fact that the function was discontinuous. So this part is discontinuous. And again, from lesson 5 or it must have been 6, because that's when we talked about differentiability. So in lesson 6, remember, discontinuous implies derivative does not exist here, or not differentiable. Okay, so if the derivative does not exist, we can't have an equal sign on the inequality at pi over 2, because it just doesn't, it's not defined there. So this is why neither inequality has those inequalities with an equal sign. Okay, so that can be kind of tricky, so if that's confusing, make sure you're asking questions. Okay, so far we found the first derivative of some functions. However, it's actually possible to take the derivative of a derivative. So we call these derivatives higher order derivatives. So it's possible to have a second, third, fourth, fifth. Some functions it's possible to derive it infinitely or differentiate it infinitely. Some functions it's not. So we call these higher order derivatives. And what we do for notation is we just keep adding primes to signal how many times we've taken the derivative. So remember, the first derivative we did f prime of x, so second derivative would just be like f double prime or f triple prime for the third derivative. But after the third or fourth, we typically kind of just write the number. So we write the number as sort of like an exponent on f in parentheses, so that we know it's not an exponent, it's actually a differentiation indication. Okay, so under the box for the first example, so that was my fault. We just want to do the first example because we don't really know how to do the second example yet. So we're going to go back to that first example that we did and take the second derivative. So if we go back up to the top, that first example was cosine of x plus e to the x. And we got as our derivative f prime of x equals negative sine of x plus e to the x. So for the second derivative, I'm just going to write f double prime of x, and I'm going to repeat the process that I did for the example. So we can think about taking the derivative of this function one term at a time. So the derivative of negative sine of x will be negative cosine of x, and the derivative of e to the x will be e to the x. So our second derivative is negative cosine of x plus e to the x. Okay, so that's all there is to it. So if you wanted to do a third or fourth or fifth derivative, you just keep repeating that process and adding primes to the notation. Okay, so from here, you're just going to work in groups and practice taking some really simple derivatives using the table on the 3 problems below, and make sure before you leave class or before you're done with this video that you check your understanding here. Okay, other than that, that's the end of this lecture.